Okay, so let's start. So we were just phrasing last time. We were phrasing the quantitative version of the fundamental theorem. So we had the fundamental theorem of statistical machine learning, and we were talking about the quantitative another T version. Okay, so what was the quantitative version? We said that if I have a class, let H be any class of binary valued functions over some domain, and assume its VC dimension is some finite number D, then there exist two constants, C1, C2, such that we have three statements. One was that about the PAC learning rate of epsilon delta. The second one about the agnostic PAC learning rates of epsilon. And the third one was about the uniform convergence rates. It's all for this H of epsilon delta. So this is about how many samples do I need to PAC learn, how many samples do I need for agnostic PAC learning, and this is how many samples do I need from uniform convergence, which in particular tell us how many samples do we need for ERM learner. So here we got something that the lower bound was something like D plus log or ln 1 over delta. It doesn't matter, divided by epsilon, and this was C1. And here I had C2 and had something very similar, but I had here this factor of log 1 over epsilon plus log 1 over delta divided by D. And here we had C2 D plus log 1 over delta divided by epsilon square. And here we had the same thing.
It should be epsilon, not D, right? On the PAC learning?
D log.
The denominator.
Yeah, thank you. Okay, that's a point. That's a point for your, thank you. Very nice. So you send me an email and you get your bonus point. Right, it should be epsilon. And here I had something very similar, C1 D log 1 over delta divided by epsilon square, and the same thing for uniform convergence. So we had those three statements. And I want to talk about the proof of those statements because those statements are very important. Yes?
Is it log or ln?
Okay, that's a good question, but the difference between log and ln is just a constant. So I can write it with log or with ln, it just will change my constant C1, C2. If all I claim is there exists constant and I don't tell you what these constants are, then it doesn't matter if I do log or ln. And I didn't bother with the exact value of those constants, but the constants are not huge. They are in the order of 100. Okay, so what I want to do today is talk about the proofs. And there's lots of things to say about the proofs, because we have here 6 statements, 3 lower bounds and 3 upper bounds. So I will not give you the exact proofs, but I do want to give you an understanding of why those things are correct. How come the VC dimension is so intimately related with the number of samples that I need for learning? So let us start by considering this lower bound. So here we are in the realizable setting, and we want to show that if you have a class of VC dimension D and you want to learn it up to a precision epsilon, you need roughly D over epsilon many points. Now, what do we already know? So we talk about the proof ideas, or proofs ideas, because we have here lots of things to prove. And the first thing I want to show is to discuss this MH of PAC epsilon delta that is greater than some constant, and here I have D plus log 1 over delta divided by epsilon. And what I want to focus about is the relationship with D and epsilon. Not so much the delta, it's not a very important part of it. So what do we already know about the lower bound for sample complexity of learning in the PAC model? We already have some kind of a result like that. Yes?
The no free lunch theorem?
Exactly. Very nice. The no free lunch theorem. The no free lunch theorem already told us something. The no free lunch theorem told us that if I put here a quarter and a quarter, or what was it? 1 over 8, 1 over 8, and 1 over 8, then what I need here is at least D over 2 many points. So the no free lunch theorem can be rephrased as saying that MH PAC of 1 over 8 is at least D over 2.
Isn't it the size of H over 2?
No, it was the size of the domain. You remember, I had the domain points,
Oh, right, okay.
and I said I have to hit. If I hit only half of the domain points, then I have no clue what's happening in the second half. But it's not the domain points, it's a shuttered set. It's a set over which we have all possible behaviors. So if I have a shuttered set, the size of the shuttered set is the VC dimension.
Okay.
So I have a shuttered set of size D, and the claim was if I have a shuttered set, all possible behaviors here are candidates. So if I hit only half of them, I have no clue what is happening in the second half. So on average, on a random point, it will, with probability half, fall here. And if it falls here, I make an error with probability half. Right? So this was D. This was the size of a shuttered set. So we got this is bigger than D over 2. OK, so now how can we, what is missing between the result that we already have and the result that we want to have? We want to show, the point is that note that as epsilon goes down towards 0, this number grows to infinity. Right? If I divide it by 0.01, it is like multiplying it by 100. So I have to show you that not only I need at least D over 2, but if I want precision roughly 0.01, I need 100 times D. So how can we make this proof force me to have a sample of size 100 times D? If I have 100 times D, then I'll see all the points and I'll know everything. So does anybody have an idea how can I push this proof to show? I mean, I'm going to use a very similar proof. But I want to push it to show me that if I want to get higher precision, I may need 100 times D points. 100 times D points. I'm going to visit all of them 100 times. I mean, how come I don't know what the function is yet? Yes?
Well, what's epsilon psi
What do you say?
So put some epsilon inside the function
No, what I want to prove is that if I put here epsilon equals 0.01, then here I will need this divided by 0.01, which is roughly 100 times the denominator, right? But I'm asking about how can we argue such? How can we prove it? Sure, the theorem implies that I will need 100 times d if I want to get precision 0.01, right? But what kind of argument can we use? Because if I have, here we use the fact that if I only had a sample of size d over 2, I'm sure that there are half of the points that were not hit, and I have no clue what's happening there. But now I want to boost this proof to show me that even if I have 100 times, I still have a large probability of error. So in order to show this, we have to remember one more aspect of this number mh of epsilon delta. mh of epsilon delta should suffice to learn to this precision with respect to any probability distribution. Here, we were just looking at the uniform probability distribution over the shattered set. But we want to see what number of samples do we need to guarantee success with respect to any distribution. So I can make a distribution that will make life harder for me. How will I make a distribution? So you see what the trick is? For the uniform distribution, if I see 100 times d points, I saw every point, and I know the function. But maybe there are distributions for which it will be harder to get epsilon precision. So what is going to be a distribution that will make it harder for me to make epsilon precision? The trick is going to be that I'm going to take those. So here is a shattered set. H has VC dimension d. I pick a shattered set. So again, pick a set A of size d that is shattered by H. So we start with the same thing. We pick a set A which is shattered. But now I want to make sure that you're going to make a big error even after you saw 100 times d points. So the set A has points, say, x1 up to xd. This is my set A, and it's shattered. So my trick is going to be that I'm going to create a trap. I'm going to take one point and give it a lot of weight. What will happen if I give one point a lot of weight? When I take a random sample, it's likely to hit this point. And when I take another point, another sample, it's likely to hit this point again. So when I'm taking my sample more and more points, with high probability, I'm seeing the same point over and over and over and over again, and I'm not getting any information about the rest of the points. So you see what may get wrong here. So I will take one point and give it a lot of weight. Now, I can go extremely far. What will happen if I put all the weight on one point? So I will see the sample, and the sample will tell me just this point over and over and over again. I have no clue of what's happening here, but do I succeed or fail in my learning if all the weight is sitting here? What do you say?
You succeed because you don't care about the rest.
Right. I succeed because I don't care about the rest. So I need to have a balance here. I want to have a trap point that will attract a lot of samples, but still I want to care about the rest. I need to put some weight of the rest because otherwise I don't care about the rest, so I don't mind that I haven't seen it. So what I'm going to do is I'm going to put 1 minus epsilon of my weight on this point, and the rest, epsilon weight, I will distribute evenly among all of those points. So here I'll put epsilon of the weight. So I'm going to use a distribution such that P of x1, the probability of seeing x1, is going to be 1 minus epsilon, very high probability. And for every I between 1 and d, p of xi is going to be epsilon over d minus 1. I evenly distribute the rest of the weight. I have an epsilon weight left in my hand. I put most of my weight I put on the first point. I have an epsilon weight left to play with. I distribute it evenly among the other points. And p of x equals 0 for any x outside my shattered set. So I have some domain, I have a shattered set, I define a probability distribution that just sits on the shattered set, but is highly tilted towards one point. Now we can use what we already know from the no free lunch theorem. I know from the no free lunch theorem that I have to see at least half of these points in order to be able to predict the rest of this part with accuracy a quarter. So by the no free lunch theorem, I can just apply the no free lunch theorem to what is happening here. I will ignore the points that are hitting the x1. They are not informative. They give me the same information over and over again. Same point over and over again with the same label. Right? But I'm just looking at what is happening here. So what is happening here, that I know from the no free lunch theorem that if I see here less than half of the points, then the probability, the relative probability of making an error here is going to be a quarter. So by the no free lunch theorem, as long as a sample hits the rest of the points, x2 up to xd, at most how often? How many times? D minus 1 over 2 times. As long as I hit only half the size of this set, right? The probability of making an arrow over this x2 up to xd, the expected arrow, is at least a quarter. So our expected arrow with respect to p, how much is going to be? See, so on this set, given that the test point comes from this set, I'm going to make a probability of expected quarter. This is given that the test point comes from here. But the test point is not necessarily coming from this set. The test point is drawn over this full distribution. So what is my probability of error when the test point is drawn according to p? Yes?
Epsilon over 4 times d minus 1? Oh, sorry, epsilon over 1.
Epsilon over 4 times what? I mean, I have a test point, right? With probability 1 minus epsilon, the test point falls here, and I know everything. With probability epsilon, it falls here. If it falls here, then we know that our expected error is roughly a quarter. So it's going to be epsilon over 4. My expected error, I mean, given that I'm in this sparse area, my expected error is a quarter. But the probability that I'll be in this sparse area is just epsilon. So in total, my probability of making an error is the probability of hitting the sparse area, which is an epsilon, times, if I hit this area, I'm making quarter error. So my probability of error is epsilon over 4. So in order to get an error better than epsilon over 4, I have to hit this set at least d minus 1 over 2 times. But how many sample points do I need in order to hit this set so often? What fraction, when I'm taking a sample over and over again, if I'm picking m points in my sample, how many of them are likely to hit this area? Yes?
Just a question, is this with or without repetition?
It's with repetition. Yeah, it's with repetition. Which we're just drawing each time IID. IID means I ignore the past. I don't know if the point was picked before or not, and I pick it again. Yeah? Yes? Right. So epsilon m of my points are going to, only an epsilon fraction of my points are going to hit this area. So only epsilon m, roughly, in expectation, epsilon m of a sample of size m will hit the important area x2 up to xd. So, in total, in conclusion, to get error, expected error below epsilon over 4, we need at least, we need that m times epsilon being bigger than d minus 1 over 2, which means m greater than d minus 1 over 2 epsilon. So we got the behavior that we wanted here. In order to get, I mean, it's only by constant factors different. Instead of epsilon here, I have epsilon over 4. And instead of this number, I have d minus 1 over 2 epsilon. It is all swallowed by this constant here. So what we showed is that if we want to have a sample size that is guaranteed to work on any data distribution, if I want to drive the arrow towards 0 to make epsilon very small, I need to increase my sample size at a rate which behaves like roughly d over epsilon. You see, I showed you that for arrow epsilon over 4, I need here d minus 1 over 2 epsilon. So if I want here epsilon, and not epsilon over 4, but just epsilon, then this will be d minus 1 over 8 times epsilon. Yes?
How does delta fit into this proof?
Right. So the delta, that's a good question. How does delta fit into this proof? But all I was talking here about is about the expected error. And you have in assignment 1 a question that shows you that there is a very tight relationship between the expected error and the epsilon delta. So this game of how to translate from the expected error to epsilon delta, I left it for you to as part of the assignment. So intuitively, it doesn't matter if we talk about epsilon delta or we just talk about the expectation. There are two ways of measuring my success. One is this epsilon delta way. What is the probability that I will not make error more than epsilon? And the other one is the expectation way. What is the expected value of my error? And those two ways are equivalent. Yes?
So how is this formula different from Hopkins inequality? There was a formula for that, for giving a sample size.
The Hopkins inequality tells you that it's exactly in the other direction. The Hopkins inequality tells you that a certain sample size suffices. It's an upper bound. Here we showed that a too small sample will not suffice. Hopkins inequality tells you if the sample is big enough, it's going a good job. Here we showed you if the sample is too small, it is going a bad job. It's the opposite.
It's the lower bound?
It's a lower bound, right? Because now we are handling this part here. The lower bound. Any other questions at this point? So this is the kind of arguments that you should be able to do, say, in the assignments. In the exam, I'm no more forgiving. I mean, I realize that in an exam, people are not always, highly focused, and there's limited time. But this level of argument, I expect you to be able to do in assignments. So if you feel that this is way over your head, then maybe it's still time to drop the course. But also, you're completely encouraged to come and ask me questions either now or in my office hour or go to the TAs and so on. I'm just saying this is kind of the level of sophistication that I expect. Are there any more questions? Yes?
What is the epsilon here?
What?
What is the epsilon in this proof? Because this is not the same epsilon.
No, it's the same. I'm looking here at the expectation over S coming from P to the M of LP, or the arrow of A of S. The expected arrow. And I'm saying for this to be less than, for any epsilon, for this to be less than epsilon over 4, we need that M will be bigger than D minus 1 over 2 epsilon. That's what we showed now. The epsilon delta said what is the sample size that you need so that with probability less than delta, the arrow is not bigger than epsilon. But it's the same epsilon. It measures your arrow. Okay, so now we handled one of the lower bounds, and I also have this lower bound here that contains epsilon square. And I want to show you in a very sketchy way why, the division by epsilon square gives me a much larger number, right? If epsilon was 0.01, then dividing by epsilon is multiplying it by 100. But dividing it by epsilon square is multiplying it by 10,000. It's a much larger lower bound. So the question is, why is it so much harder to learn in the agnostic case than in the realizable case? So rather than giving you a proof of this lower bound, I'll just try to explain why are things getting so much harder when we are in the agnostic case. So why do we need so many more examples for learning in the agnostic case? So what is, first of all, let us recall what is the difference. The PAC case, we assume that one of the functions in my class had 0 error. Now I don't make such an assumption. If I don't make such an assumption, let me just demonstrate one kind of problem that we may need to solve. So assume that we have a situation like this, that my domain consists of only 2 points. There are only 2 points in my domain. So what could be the maximum VC dimension here? Yes? Just 2. Only 2 points in my domain. But now I can define a probability distribution. I don't just give you a labeling function and the distribution over the domain, but I have to give you the probability of each point getting 0 and the probability of each point getting 1. So let us give these points names. Let's call them x and y, very original names. And let's say that my probability define a probability distribution like this. P of seeing 1 with x is going to be say P of, okay, let's start, let's do it, even break it down into more pieces. So define a probability distribution by picking each of x, y with equal probability, which is going to be half. And now I have to tell you how do we pick the labels, right? I have to tell you how do we pick the labels. So the probability of having label 1, given that I saw x, the probability of having label 1 is going to be half plus some small number, very small number. Let's call it epsilon. And the probability of seeing 0, given that I saw x, what is it going to be? If I see x, then I either see a 1 or see a 0. So if I gave you the probability of seeing 1 given x, what's the probability of seeing 0 given x? Yes? Right. Half minus epsilon. And vice versa for y. So the probability of seeing 1 given y is going to be half minus epsilon. And the probability of seeing 1 given seeing 0 given y is half plus epsilon. Okay, so I have 2 points. I am evenly likely to pick each of them. But one of them, if I picked it, I'm a little bit more likely to see 1. And the other one, if I pick it, I'm a little bit more likely to see 0. Now I want to tell you what is my class. So my class is going to be the 2 functions. My class H is going to contain 2 functions. The function Oh, yeah, I can even have all four functions. All 0, 1 functions over x, y. I only have 4 functions. I have the functions 1, 1. I have the function 1, 0. I have the function 0, 1. And I have the function that gives both of them 0. These are all my possible functions. Now tell me, which is the best function here? Yes? Well, the best function is 1, 0. Because this guy is a little bit the base function. The base function is 1 for this guy and 0 for this guy. So the best predictor in this case is the function 1, 0. And this is also the base predictor. Right? Remember, the base predictor, the optimal predictor, is the one that for every point gambles on the label that has probability greater than a half. But now I'm just giving you samples from these points. And now what do you see? You see a point and you see either 0 or 1 label. You see another point, you see either 0 or 1 label. In order to be able to tell me that this point is more likely to get 1 and this point is more likely to get 0, what you basically need to be able to do, it's like that I'm holding a coin in my hand. And the coin is biased towards heads. Slightly like half plus epsilon times will get you head, and half minus epsilon all the time will get you tail. Now I'm beginning to toss the coin, and I want you to tell me, is it biased towards head or is it biased towards tails? Because in order to find the best predictor, it's like that each time I draw a point, either I toss a coin here or I toss the coin here. And you need to decide for each of them if it's more likely to be head or tail. And each of them has a small bias. So in order to be able to find the good predictor here, you need to be able to tell me if a coin with a small bias, which side is it biased towards. Now, if I pick a wrong predictor here, how big is my error? It's not difficult to calculate. If I pick a wrong predictor. So this guy is the best one. This is best. If I pick any other of them, what is my probability of error? Yes. The probability of error is, it could be epsilon. It could be just epsilon. Because if the wrong guy differs for me, it's this one, then I'll make an error only if I hit the y point. And if I hit the one y point, my probability of making an error is 1 plus epsilon compared to 1 minus, half plus epsilon compared to half minus epsilon. Right. Fair. So with this guy I have 2 epsilon error, and with this guy I have only epsilon error. And I don't do the calculation on the board because I leave it to you. I want you to make sure that you can do such a calculation. So in order to get epsilon error, I really should be able to pick the correct guy among them. Because if I pick the wrong guy, I make error more than epsilon, or at least epsilon. But to pick the correct guy, I must be able to, I have to ask, I'm asking you how many sample points do I need to see? I need to see enough sample points to be able to distinguish if you have a coin with a small bias, in which direction is the bias going. Yes? What? No, so it turns out that this probability, right, so it turns out, and this is something completely from probability theory that I'm not going to get into. In order to detect if a coin has bias half plus epsilon towards head, or 1 plus epsilon towards tail, one needs roughly 1 over epsilon square coin tosses as epsilon gets small. Of course, if epsilon is big, then one coin toss will tell me the answer, right? What? No. Either or. Right, or. Right, okay? So this is a result from probability theory. If I want to be able with, again, it's an epsilon delta kind of result, and we can give a precise formulation, but I'm just going to get the flavor of it. If you have a coin, the coin is very lightly biased, you will need a lot of flips of the coin in order to detect which way it's going. And this is going to require 1 over epsilon square coin tosses. So in order to learn with probability epsilon in this very simple situation of agnostic learning, we will need at least 1 over epsilon square sample points. Each sample point is like tossing a coin. It's picking one of the points and tossing a coin to decide the label. And that's why we have the epsilon square in the denominator in the agnostic case. Of course, now one have to take this component and build it into a proof that contains the visit dimension as well, and so on. But that's not the interesting part. The part that involves the visit dimension, we've already seen here how to handle it. The difficulty is coming from just deciding on one coin. Okay? So all I wanted here to do is to give you some intuition of why is it so difficult to do the agnostic case. And there's something else that we can learn from this story, is that the agnostic case is getting harder when we are getting further from being deterministic. If these were coins with big bias, then I wouldn't need 1 over epsilon square coin tosses to decide it. It is just because the bias is very small that we need so many examples. But the agnostic case say you have to be able to handle any probability distribution, so you also have to handle probability distributions that have very small bias. So that's as far as I'm going to talk about the lower bounds. And before I switch to talking about the upper bounds, I just want to give you a chance to ask questions. All clear? You're all in? Yes?
So what does it mean that you need that many? Because technically, no matter how many coin tosses there are, you still can't tell absolutely for sure. So
You never can tell absolutely for sure, right? There's an epsilon, there's a delta thing, right? So it's a very good question. I mean, because what she was asking, she says, what does it mean how many coin tosses you need? No matter how many of them you toss, you never know for sure. But the question is, how many do I need to get a probability of failure no more than delta? And it goes back to basic probability theory. Because if I draw the distribution of, if I just toss one, if I toss a coin once, and I look at the distribution, then with probability, so here I'll have the probability, and here I'll have the values that I see. So this is the value 0, and this is the value 1. If I toss the coin point only once, then I'll have half the time I'll see just a 0, and half the time I'll see just a 1. If I toss the coin 2 times, then suddenly I'll see something different. I'll see a quarter of the time this guy, half of the time this guy, and quarter of the time this guy. If I toss the coin 100 times, it will look like something like this. The more times I toss the coin, the sharper it becomes, and this is centered just around the bias of the coin. And we want to be able to distinguish between bias 1/2 plus epsilon and bias 1 minus epsilon. They're very close. So I need a lot of coin tosses such that this be sharp enough such that I have much higher probability of being close to the correct answer than to being close to the wrong answer. Okay, so that's the intuition of what is happening here. As we toss the coin more and more often, the distribution of the average that you will get gets concentrated, more and more concentrated around the exact bias of the coin. If I want to detect the exact bias to within some precision, I need it to be very concentrated. I will still have misleading, even if the bias is here. I will still have some misleading samples that will give me completely wrong answer. I want to bound this case by probability of delta. That the probability of falling in this tail is at most delta. So the more coin tosses, the sharper it gets, and the smaller the probability of being in this misleading tail. Okay? That's the intuition of what's happening here. But we're never completely sure. That's why our bounds involve delta as well. Yes? Okay. So those lower bounds are kind of the less interesting part of the story here. Because as you see, my lower bounds are just have to do with classic probability theory. We are tossing coins, we have points, we count how many times we hit them. It's kind of classical probability theory. We didn't really use the VC dimension. The only way we used the VC dimension was we said we have this set on which we have all possible behaviors. The upper bound is where machine learning comes into the game. Because the lower bound is saying, oh, you can't learn. Can't learn. We knew it before. You don't have to go to a machine learning course to be pessimistic. We want to come up with optimistic results. You can learn. You can do something. And that's where the upper bounds come in. And the upper bounds are based on a very special property of the VC dimension. There's something nice about it. So that's what I'm going to talk about now. And this is called the Sauer lemma. But before I'll tell you about the Sauer lemma, so this is, as a topic, what we are going to talk about now. It's called the Sauer lemma. And this is the key property of VC dimension that makes this all tick. But before I can talk about the Sauer lemma, it's like before I could define VC dimension, I need to define shattering. Before I can talk the Sauer lemma, I have to talk about some intermediate definition. So we have a definition of the shatter. What, shatter? Now suddenly, shatter was U or A? A. The shuttle function. Okay. Okay. So what is the shuttle function? Given a class of binary valued functions H over some domain set X, we define a function pi of H, and this is a function that goes from the natural numbers to the natural numbers. And what does this function do? For every number m, I need to tell you what is pi h of m. So for any number m, pi h of m is the maximum over all subset A subset of X such that the size of A is M, the maximum of the size of the set H, the set of all H intersection A such that H is in H. Okay, so let's try to read it, see what we're saying here. So I'm picking some number M, and now I'm going over all subsets of my domain of size M. And for each of them, I ask, how many pieces from A can capital H cut? So it's kind of reminiscence of the shattering. But the shattering said A is shattered if I can cut with H every possible subset. And now I'm also considering the case that it's not all possible subsets. I'm just counting. How many subsets can you cut? Does it make sense? I look at all sets of size M, and I ask, how many subsets of A can you cut? Let us start with some simple observations that will kind of create, hopefully, generate some intuition about this function. So here are some simple observations. Some simple observations. The first one is that for any H and any M, pi H of M is always at most 2 to the M. Why is that the case? I'm saying this function is always upper bounded by 2 to the M. Why?
It's the number of all possible subsets.
Right. In the best case, I'm cutting all possible subsets of A. And the set A of size M has only 2 to the M many subsets. But now we can see something that relates to shattering. So if, observation 2, if H shatters a set of size M, then what is going to be pi H of M? If there is a set of size M which is shattered, then what am I going to get? 2 to the power of M. If I shatter a set of size M, then I'm getting exactly 2 to the M. I get all its subsets. In general, it's at most 2 to the M. And what happens if the VC dimension of H is less than M? Then what do I know about pi H of M? Yes? Right. Because VC dimension less than M means I don't shatter any set of size M. I don't shatter any set of size M. It means for any set of size M, if I try to cut all the 2 to the M subsets, some of them I will fail. So if I just count how many can I cut, it'll be strictly less than 2 to the M. So we see that it is kind of very related to the VC dimension. If we try to draw it in a graph, so here I'll have pi H of M, and here I will have M, and say this is VC dimension of H. then what do I know? I know that it goes like this. This is the function 2 to the m. Then I get to the vice dimension. And here it goes a little bit slower. Because if I shatter a set of size d, I shatter also smaller sets. I shatter all subsets of it. So it's 2 to the m all the way up to the vice dimension. When I get to the vice dimension, it is getting below 2 to the m. If this is 2 to the m, my function now goes like this. This is the Shuttle function. It behaves like 2 to the m up to the vice dimension. Then it is somewhat below the vice dimension. And what you want to ask is, how much below is it going to be? So this is there is a very nice result here. And the result basically says, that I don't know how many of you have taken courses that you talk about asymptotic runtime of some algorithm. We usually say that algorithms problems are either exponentially hard, which means the runtime is more than 2 to the n, if n is, or if they're not exponentially hard, what are they usually, those problems? Polynomial. So in roughly, if you just go to computer science classes, you can think that functions can be either exponential or polynomial. But in the reality of mathematics, there could be many things between them. Can you give me functions which are between being exponential and polynomial? So exponential is something like 2 to the m, 2 to the m, 3 to the m, I don't know what. Polynomial is m squared, m to the power 4, m to the power d, and so on. And somehow in computer science you can get the wrong impression that there's nothing in between. But there could be many things in between. So can you give me an example of something in between? Give me, yes.
M2 to the power of
M?
m squared to the power of m2.
Oh, it'll be above this.
Yeah, this is in the power.
Yeah, I want to be between them. I don't want to be above exponential. I want to be below exponential, but still above polynomial. Yes? 2 to the log m. What is 2 to the log m? Can everybody tell us what is 2 to the log m? 2 to the log m is just m, right? So what can happen in between? What? You want to take a weight from each. There are many things in between. But anyway, this is going very slow. This is going up very far. I can do things like m to the log m. You see, I can take here, if I take m to any exponent, which is less than this, but more than a constant, any function here that grows with m, it is not a constant, so it will not be polynomial. But if the function does not grow fast enough, it will not be exponential. If the function here is below m, then I will be in between. So I can have here log m, I can have here log m, I can have here log m square. The fact that I cannot come up with many interesting functions here doesn't mean that there aren't many. It's a huge range. But somehow in computer science, there is this dichotomy. Either things are hard, then they're exponential, and all things are easy, then you call them polynomial. What I want to call your attention is that there's a whole world between them. And why do I comment about it now? I could make this comment at any time, because the Shuttle function is maybe one of the very few, if not the only example, in which this is really a dichotomy. Turns out the Shuttle function is exponential up to m, but from here on, it becomes just m to the d. So it is maybe the only case that we know in computer science of something that really has the dichotomy. It's exponential, and then suddenly it becomes polynomial. And it doesn't allow any intermediate behavior. That's basically what the Sauer lemma says. So let's see the exact formulation. So we are going to claim that this Shuttle function is very interesting. It climbs very fast, hits the VC dimension, and suddenly it loses all of its energy and it starts climbing very slowly. OK, so let me state the theorem, and then I'll show you some consequences, and I'll show you the proof, because it is such a nice theorem that I cannot resist the temptation to show you a proof. So there are many interesting things about this Sauer lemma. And the first interesting thing is how it was discovered. So the Sauer lemma was discovered around 1970, 1971. And why do I give you this rough estimate? Because it was discovered at the same time, roughly the same time. And I mean, for you, 1970 is ancient times. But for me, it's not so ancient times. But in these times, we didn't have internet. And when someone got a result, they wrote it on a real paper and sent it around to their friends. And they will have to wait for the mail to reach there. And if the result... So people in different locations did not have very good communication. So it turns out that exactly at the same time, the same result was discovered in many places. It was discovered by Vapnik and Chervonenkis, the guys from the dimension in Russia. So it was then USSR. And it was discovered, of course, by Sauer. And I think he was in the UK. And it was discovered by Shelach at the Hebrew University in Jerusalem. He later he was my supervisor for my PhD. And it was also discovered by another guy at the Hebrew University, which his name is Perles, also in Jerusalem. And it actually was discovered by Perles twice. So it should be called the Vapnik, Chervonenkis, Sauer, Shelach, Perles lemma. I mean, he discovered it and wrote a paper, and then forgot that he already knew it and discovered it again. So, OK. So, but somehow it became famous as the Sauer lemma. The interesting part from the point of view of history of science is that at least 3-4 different people, without communicating with each other, discovered the same result at roughly the same time. And each of them for completely different purposes. I mean, Vapnik and Chervonenkis are statisticians. Sauer was doing combinatorics. Shelach was doing model theory. I will not tell you what model theory is, but it's completely unrelated to combinatorics or statistics. And Perles was also doing combinatorics. So these two guys have a similar interest, but these guys have completely different interests. And all of them at the same time discovered the same lemma. OK, so see how much of a teaser I gave you about this lemma. It gives you this exponential polynomial duality. And there's a nice story about how it was discovered. And now let's get to the lemma. And the lemma is that for every class H, and every D, if VC dimension of H equals D, then for all M, pi H of M is at most the sum I goes from 0 to D of M choose D. Yeah, this looks pretty ugly, but let me immediately replace it by something more. This is always at most m to the d. Now, so this looks that the Shuttle function is always polynomial in M. So how can it be exponential? If this is a theorem, how can it be exponential at the beginning? Yes. No, I don't need even asymptotics. What I'm saying is that if M is less than D, then this is exponential in M. Because if M is less than D, that I'm allowed to have here M. If M is less than D, I'm allowed to have M in the exponent. It will still meet the bound. So for M less than D, it's allowed to be exponent. I can have M in the bound as long as in the exponent as long as M is less than D. Okay. Yeah, what's the question?
Well, no, I just want to say why.
What?
I just wanted to say, like, why is it exponential at the beginning?
Ah,
Just the binomial theorem, like, just 2 to the power. Is the binomial theorem just 2 to the power of n?
right. Very good. This is the binomial theorem. So if I allow this to go up to M, then I'll get here just the sum of all binomial coefficients. It'll be 2 to the m. So if I showed you equality here, less than, this tells you this is the number of subsets of M that have size at most D. So if I allow D to be bigger than M, it's the number of all subsets, which is 2 to the m. If D is smaller than M, then it's a number of all small subsets. So it's less than 2 to the m. Yeah, very good point. Yes?
Sorry, the subscript I, where is that in the rule?
Oh, very good. This is great.
Oh.
This is I, and this is a bonus point if you're taking the course for credit. Right. It is, so this is the sum, this M choose I tells me how many subsets of size I do I have. And if I take the sum or summation over all i's, it tells me how many subsets do I have of size at most D. This tells me how many subsets do I have of size exactly I. If I sum over all i's up to D, it is how many subsets do I have of size at most D. Right? And if D is above M, it is just how many subsets do I have, which is 2 to the m. Okay, so fix it. It is I, not D. Very good point. So before we go into the proof, which I still want to show, because there was kind of, for a while, each of them came, first of all, I mean, we had so many authors. Each of them came with a different proof. So Perles came with 2 different proofs. That's why he didn't realize that he already proved it before. And each of them had a different proof. And for a while, there was a competition of who has the shortest proof for this theorem. And I'm going to show you a proof that is only 3 lines. The problem is that it needs a lot of explanations for these 3 lines. But it's a, OK. Before we go to the proof, let me just show you why this is, in what sense it's interesting. So one corollary, which is really has a lot of implications, is on the number of partitions realizable by a linear half space. So what do I mean here? So assume that I have a pizza. And on my pizza, I have all kinds of stuff. So I have here, I don't know what, a green olive. I will not try to draw it. And I have here a black olive, and I have here a mushroom, and I have here a tomato, and I have here onion, And I have here, we can add some meat also. So I have kind of salami here, all kind of stuff on my pizza. And I want, someone tells me, you know what, I like green olives and I like tomatoes, but I don't like salami. Can you cut me a piece that will contain what I like, but not what I don't like? And I want to cut this pizza with a straight line, because I have this cutter, and give him what he wants. So what I'm asking is, how many such partitions, how many idiosyncrasies of my guest can I accommodate? Can I, for every combination of I want this and not this, and this and not this, and this and not this, can I find a linear cut in my pizza that will satisfy my guest and give him exactly all the ingredients that he wanted, but not the other ones? That's what I call is the number of partitions that are realizable by a straight line, by a linear half space. And the point is, what will be your intuition? If I have, say that I have lots of points, I have a set with many, many points in the plane. And I say I have here, in my set, I have 1,000 points. What do you think? And now I can think about all possible partitions of those points. How many of those partitions, what fraction of those partitions are going to be realizable by a straight line? So I'm partitioning my points into black and white. And I ask, how many black-white colorings do I have that can be separated by a straight line? Is it going to be most of the black-white coloring, or it is going to be only a small fraction of the black-white colorings? Yes? It's going to be a very small function. So what I'm claiming is that the Sauer lemma, and it's related to the Sauer lemma. So the number of colorings that I can get with a straight line is related by the Sauer lemma. Why is it related to the Sauer lemma? Because if I have here a set of 1,000 many points, this is some A of size 1,000. And I know what is the VC dimension. I mean, if I want to cut it with a straight line, I need to know what is the VC dimension of the class of all straight lines in the plane. So we know that the VC dimension of straight lines in dimension 2 is 3. I mean, we talked last time about the uniform, about the homogeneous half spaces. If I allow them to go everywhere and not necessarily through the origin, then I get here n plus 1 rather than n. Remember last time we said that H half spaces n that go to the origin have this dimension n. Half spaces in general, VCD of half spaces for general, not required to go to the origin, is n plus 1. You will prove it in the next assignment. So what does it mean? It means if we apply the Sauer lemma and we ask how many ways do I have to cut 1,000 points with a straight line, it is going to be at most, so number of ways to cut a 1,000 item pizza by a straight line. By the Sauer lemma, it's at most the number of points that I have on the pizza to the VC dimension. So it is at most, this is the Sauer lemma. It's at most 1,000 to the power 3. Because my VC dimension of all lines in R2 is just 3. But how many, what is the number of black-white coloring of those 1,000 points? How many ways do I have? Yes? 2 to the power 1000. So here I have, just if you want to compare these numbers, here I have 10 to the power, how much? 10 to the power 9. And here I have roughly 10 to the power 300. So the number of ways to separate with a straight line is a minuscule, like negligible fraction of the number of ways that I could separate points. And this is a consequence of our Sauer lemma, because in order to deduce it for a Sauer lemma, all we needed to know is that the VC dimension of the class of all half space is 3. And this is exactly this wonderful dichotomy that I was talking about. We talk about pi h of m. Here we go up to 3. Up to 3, it's 2 to the m. So here we get 8. And from here on, it goes much slower. It's only m to the power 3. So if we hit here m equals 1000, this guy is way over the ceiling, maybe third or fourth floor. It's 10 to the 300, while this guy is only 10 to the 9, which is also third floor. But you see, so suddenly we see how big, how dramatic is this bound. The minute you cannot shatter all of the sets, the minute you cannot cut all of the set, immediately the number of sets that you can cut falls way, way below the maximum number. Because you could say, one could think initially, sure, this shuttle function, if you get 2 to the m, then you shatter m points. But if you don't shatter, maybe all you get is 2 to the m minus 1. Or maybe all you get is 2 to the m minus 1. Or maybe all you get is 2 to the m over 2, many subsets. But the Sauer lemma tells you the minute you don't get the full 2 to the m, it's less than this and less than this and less than this. It's way, way, way less. It's only polynomial. Suddenly there is a big drop in the number of sets that you can cut. So in that respect, it's a very surprising lemma. OK, I don't have time for the proof. I do have time for a quick question, if anybody has. I mean, that's the kind of time in the class that I could do now the proof in 1 minute and nobody will have questions about it, right? OK, so we'll see you next week. Have a nice weekend.